crystal vibrations in terms of the complementary concept of particles. So far we have treated the oscillations as waves inside the solid, in which the atoms about their mean positions oscillate. So that was the wave picture. But a complementary picture describes these oscillations in terms of particles. And those particles are called phonons. So in order to build the concept of phonons, I would like to go back to a dispersion relationship between the wave number and the angular frequency of these oscillations. So you can have up till the zone boundary, if you just consider a one-dimensional chain of atoms, possibly 3 atoms in the basis, you get these 3 acoustic branches. And we've also seen in the previous lecture that each of these branches is in fact digitized and broken down into discrete points arising out of the periodic boundary conditions. So there are millions of points inside each branch. And corresponding to a particular wave number k, there are frequencies associated with that k. And frequencies in each branch, so omega k1, omega k2, omega k3, and we can denote all of them as omega kr, where r is an index for this branch inside the dispersion relationship. Now, each of these dots that I've drawn here represents some natural frequency of a collective oscillation of atoms inside the solid. The number of dots in a complete Brillouin zone, first Brillouin zone, will be equal to the number of atoms inside the solid. So if there are n atoms, there will be n by 2 k points on this branch and n by 2 k points on the negative side, so n in total. And since there are 3 branches, there will be 3n total modes inside this first Brillouin zone. So each of these dots is called a mode. It represents a particular frequency, and that frequency of course corresponds to a k value and a branch index r. So this is a collective oscillation of all the atoms. Now what we could say is, and it's not the oscillation of a single atom, it's a collective unified motion of all the atoms in a particular configuration. So this mode can alternatively be described in particle language by a particle which is called a phonon. And we would say that when the crystal is oscillating inside this mode with the frequency omega corresponding to a k and a branch index r, there is in fact a particle inside the system which is called a phonon. And depending upon the amplitude of this mode, there could be 1 particle, 2 particles, 3 particles, and arbitrarily large number of particles as well. So these particles, phonons, are quasi-particles in the sense because they have some quasi-momentum h bar k, they have some quasi-energy h bar omega. I say quasi because it's not a true momentum. We do know that if we change k by multiples of the reciprocal vector, the omega does not change at all. It's periodic in k with respect to the reciprocal lattice vector. So h bar omega is not a true momentum, it's like a quasi-momentum. And these particles are called phonons. Another way to look at these particles is that if the system has a particular number of phonons, say n phonons. We can represent this by the quantum state ket n. And the phonons, this quantum state n, for a particular, at a particular frequency omega k r, says that there are n photons inside the system which belong to this mode omega k r. Okay, and this number of particles can change. So the number of particles can go up, it can go down. So particles can be created and annihilated by suitable processes. So if we kind of come back to how we describe a harmonic oscillator in quantum mechanics. If we have a potential energy of this kind, so this suppose is some space variable and this is an energy axis, and this is the kind of the potential energy that we have in a harmonic oscillator. Then if we quantize this harmonic oscillator, we see that all the energy levels are equally spaced and they are spaced by a distance h bar omega, where omega is the natural frequency of that harmonic oscillator. So phonons likewise can be described by exactly the same mathematical formalism. They look like, because of the harmonic potential, this parabolic potential that exists between the atoms inside a solid. We've already seen the potential energy for atoms inside the solid. So the potential energy we do know is given by some baseline, some equilibrium energy plus half phi nj mb s na mb s na s mb summed over all m and n, a and b. So in the second harmonic, in the second order approximation for the energy, we've already derived this relationship. So this term is quadratically dependent upon the distances, very similar to what we have for harmonic oscillator. U equals some baseline energy plus half k, a square of a distance. We also have a square of a distance here. So when these atoms are connected together by bonds or interactions, the interactions in a pairwise sense, up to second order, they can be represented by harmonic oscillator. So exactly the same potential manifold is visible inside the solid, and a particular mode, fixed frequency, fixed k, fixed branch index can therefore be represented by harmonic oscillator in which the spacing is h bar omega, and the minimum energy that exists is h bar omega over 2. So in the phonon model, we can say that the energy can change, which means in the particle picture, we say that more phonons are created. So if you go higher up in this ladder, at this level, when the energy is in the ground state, there are no phonons in the system. So this corresponds to the state ket 0, no phonons in the system. Now we can create a phonon. When we create a phonon, that is created by an operator, the creation operator, A dagger. It generates a photon, a new photon is created, and the energy of the system goes up. So if the system lies here, then we have knowledge, or we can say that there is one photon in the system. There are two photons in the system if we keep on going to higher levels. So if we start off with a single phonon, we can create yet another phonon, ket 2, and have two phonons in the system. Of course, we also need a particular normalization constant. So just using the language of quantum mechanics and these ladder operators, we can create phonons in the system. So we can go up, we can also come down. For example, if we start off with n phonons in the system, and if we annihilate or remove one photon from the system, we can lower the number of photons in this fashion. So by the creation and annihilation operators, we can move on the staircase of harmonic oscillators. More phonons can be added into the system, and phonons can be retrieved or extracted from the system. A higher number of phonons classically means that that particular mode is oscillating with a higher amplitude. And remember, it's not a single atom that is representing a phonon. It's really this entire collective excitation of atoms that is called a phonon. Now for a harmonic oscillator of this kind, we also have a very good idea of what the energy looks like. So if there are n phonons in the system, then the energy corresponding to this bath of phonons, now these phonons can really be treated like a gas of phonons. So even though we have a solid in which we are oscillations of the atoms, once we move to the second quantization picture, which is the picture which treats these oscillations as phonons, we can treat these phonons as a gas. So it's a gas of phonons. So with n phonons, the energy of the system we all know is given by n plus half h bar omega. So this is the energy of the system when we have n phonons inside the system. Now, equipped with this description, we can come up with lots of different properties that are associated with the atoms inside a crystal, which of course lie on this periodic structure that we've been discussing so far. So one of the properties that we're really interested in is properties related to thermal energy. What happens if we add energy to the system, or if we change the temperature of the system. Now, in condensed matter physics, when you create a new material or synthesize something, the first thing that you would like to do is you would like to change the temperature and see how a particular property varies or alters with temperature. So this phenomenology gives us an idea of what kind of particles or what kind of quasi-particles exist inside the system, how they are behaving, what is the phase of the system, and so on. So looking at temperature variations of properties is really important. So now there is an energy in the system. Of course, if in a harmonic oscillator we change the energy of the system by putting this system at a higher temperature, more phonons will be created. If we cool the system, the phonons will be extracted from the system. If we have this solid and we shine particles like neutrons or light particles, photons, then those photons are bringing in their own momentum, they are bringing in their own energy, they will interact with the particles inside the system, and then the probe particles will be scattered. So all of this has to conserve energy, it has to conserve momentum. So this idea of phonons is extremely powerful. So the first thing that we're going to observe is this idea of heat capacities. Now the heat capacity really tells us how the thermal energy or the internal energy, which is potential energy, changes with temperature. So if I have the energy U and I find how this energy changes with temperature at a fixed volume, this quantity is called the specific heat capacity at fixed volume. And we're keeping the volume fixed. We're not allowing for this solid to expand or contract, because in this model in which we've just truncated to the second order in the displacements, we cannot have expansion or contraction. So we are good. So if we can somehow find the total energy of the system and then differentiate with temperature, this will give us the heat capacity. How does the heat capacity change with temperature? You are changing the temperature of the system and how much energy is being added to the system. So we we all know from the first law of thermodynamics is that the change in energy of the system is equal to the thermal energy that goes inside the system plus the work done on the system. All right, so what we're trying to do is we are finding out the change in the potential energy as the temperature changes. For example, the temperature could change through external work. That is the work done by a battery in moving a current through a solid so that the solid heats up. Or you can add thermal energy to the system by just putting the object on near a heat source. So first of all, we would like to find out, we focus our attention on a single harmonic oscillator of frequency omega. Okay, frequency omega, just a single frequency omega. Okay, and find out what's the energy of this system. So from statistical mechanics, we know that if we have different energy levels as we have for the harmonic oscillator, the average energy is going to be given by the energy inside each level, and then you multiply this with the probability that the system exists inside that level, and that probability is given by E minus the energy n plus half h bar omega over kBt, where kb is the Boltzmann constant, and you need to divide this by the partition function, which is E minus n plus half h bar omega kBt summed over all n's. Right, so this much is the partition function. We call it z, represented by z. This much, this divided by z is the probability. This is the energy that exists in a particular level, and you need to in order to find out the expectation value, you sum all of this with respect to n. All n's from 0 to infinity are possible. So this will give us the average energy of a harmonic oscillator. Now, the average energy of this harmonic oscillator can be easily computed. So if you look at this z, this partition function, which sums up all of these exponential factors, we can simplify this a little bit. So let's do this simplification and let's do this calculation. So if I take my z to be this sum, I can write this as E minus h bar omega kBt. I can take this factor out as a common with a half, and then sum this from 1 plus E minus h bar omega kBt. This is n equals 0, n equals 1 plus n equals 2, and so on. Okay, so this is a geometric series, as we all know. So this z turns out to be E minus h bar omega 2 kBt divided by 1 plus E minus h bar omega kBt. So this is my partition function, and I can also, so once I have this partition function, which I can also write as E minus h bar omega 2 kBt 1 plus E minus h bar omega kBt minus 1. So this is my partition function. Now if I were to take the natural log of this function. Let's take the natural log of this function. I'm just trying to come up with a simple way of calculating this total energy. So if I take the natural log of this partition function, I will get minus h bar omega 2 kBt minus 1 over 1 plus e minus h bar omega kBt square minus h bar omega over kb minus 1 over t square. All right, so this is the natural log. So the natural log of this plus the natural log of this, the natural log of this comes out to be this, and the natural log of this, sorry, comes out as minus natural log of 1 plus e minus h bar omega kBt. Okay, so this is the natural log of z. Just give me a second. Okay, so in the next step, I take this natural log and differentiate this with respect to t. So if I were to do this differentiation, this would become h bar omega 2 kb t square t in the denominator plus minus this term comes in the denominator 1 plus e minus h bar omega kbt minus h bar omega kb minus 1 over t square. Okay. So there's a minus here, minus differentiation of this is natural log of this is this. This would give me the derivative of this term is e minus h bar omega over kbt, and then I need to find the derivative of this power, which is minus h bar over kb, and the derivative of 1 over t, which is minus 1 over t square. Okay, is this okay? So I think I'm missing a minus sign. Square over here from the geometric series. I'm sorry. This is minus. This is minus. There's an additional minus, so this would become plus. Okay, so this would become h bar omega over 2 kb t square plus h bar omega kb t square. And now look at this term. There's an exponent divided by 1 minus that exponent. So this would become, I take this into the denominator. This would become e raised to power h bar omega kBt minus 1. Okay. Therefore, henceforth, if I take this derivative of natural log z with respect to t and multiply this with t square, my final result is h bar omega over 2 kb plus h bar omega over kb and this term, which I would now like to write in a different color, 1 over h bar omega kbt minus 1. I can in fact take the kb in the numerator as well, put a kb here. All right. So now what you are able to see is that this term is equal to a ground state energy plus the energy of the phonon, of a single phonon, multiplied by this factor. This factor here really represents the average number of phonons inside the system. Okay? The factor is called the Bose-Einstein distribution factor. Let's denote this by FBE, function of omega and of course temperature. So this Bose-Einstein factor tells us that how many phonons exist inside this gas at a particular temperature, capital T. So this is the number of phonons, the average number of phonons, frequency omega. You can put a small k with this if you like, you can put an r with this if you like. This is the average number of phonons, the energy of a single phonon, just one phonon. So this will give us the total energy that exists inside that bath of phonons. So now you have oscillations and you have converted this problem to a problem of quasi-particles, that is phonons, and now you can find out a term which of course is proportional to energy. We still have to relate this to the overall energy. And now we have broken this energy into two parts. A ground state energy, which always exists, even at zero temperature, because of the uncertainty principle. And then a term that factors out very neatly into two terms. One is the energy of a single phonon, and multiply this with the number of phonons to give us the total energy. Now what we have to do is we have to relate this thing to the overall energy of the system. Now we do notice that this term will actually be equal to what I've written over there. So how do I know that? So that's very simple to see. Here, if I take this U average 1 over Z, if I take this Z, if I just took this Z and I differentiate this with respect to T, so I just take this Z and differentiate it with respect to this T, what do I get? I would get E minus n plus half h bar omega kBt minus n plus half h bar omega kb minus 1 over t square. This becomes plus 1 over t square. Okay, and then if I divide this term by Z itself, so let me simplify this a little bit. N plus half h bar omega. Of course, there is a summation here as well with respect to n. 1 over t square kb sum over n e minus n plus half h bar omega kbt. But this term is simply the numerator over here, barring this 1 over kbt square factor. So this numerator here is simply kbt square, the derivative with respect to t of z, and I already have z in the denominator. Now this, from the rules of derivatives, this term in yellow is simply the derivative of natural log of z. So this term is simply kbt square, the derivative with respect to temperature of the natural log of z. So hence, this term that we have found is really that energy U average. So what we've done is we found out the total average energy of a harmonic oscillator in a single mode. Now if you want to calculate the total energy inside the phonon system, phononic system inside the crystal attributable to second order oscillations, we just take this average energy for a given k, for a given r, sum over all possible k's, all of these k's that exist inside the first Brillouin zone. And remember, here I've only drawn the Brillouin zone in the reduced scheme. So there is an opposite branch which extends from 0 to minus pi over a as well. So you sum up over all possible k's and sum up over all possible branch indices, you will get the total energy that exists inside this system due to phonons, due to oscillations, correct up to second order. So this is the energy in the harmonic approximation. Okay, so far so good. So it has a very neat kind of breakup, factorization into the ground state energy plus the energy attributable due to the phonons. So what we would like to do next is would like to find out, we'll improve this formula a little bit further as we go along. So what we would now like to do is, with this description of a system in which we are just considering a single mode of frequency omega, let's see what is the specific heat capacity. So the calculation that we've done was first actually done by Einstein. So let me call this the Einstein model. So the Einstein model assumes really that there is only one frequency inside the system, just one frequency omega. So one kind of mode inside the system omega. So this distribution of frequencies of varying modes can be represented by a graph by another distribution function. So if I put omega here and I put a density of states, a density of modes, which means I would like to see which modes exist inside the system, then this graph, which really represents the distribution of the modes, is called the density of states graph. So this is the density of states. And the Einstein's model assumes that all of these modes have the same frequency. So just considering a single mode, in fact, just one mode, and that mode is omega. So all of the modes are concentrated on this one frequency, which I've actually called omega. This is my omega here. In all of these calculations, this is my omega. I call it omega. So this is some frequency axis, and all of the modes belong, all of the phonons belong to this mode omega. Of course, this Dirac delta function is going to have a specific density with it, a specific magnitude with it. So what you would really like to do is you take all the modes inside the system. This will give us the total number of modes. And we know that the total number of modes inside the system is n for a one-dimensional solid. It's 3n for a three-dimensional solid. It's 3rn for r branches. So this is a countable. So if I take this integral from 0 to infinity, the answer is countable. It depends upon the number of modes inside the system. So that really determines the density or the magnitude of this Dirac delta function. So the Dirac delta function on a whole can be written as, so this is my omega prime axis, so it's written as Dirac delta function omega prime minus omega. So this is the Einstein model. So now in this Einstein model, if I were to take this energy, for example, let's consider just one branch, r equals 1, and just look at a single harmonic oscillator for the time being, and then after all we'll scale the results with r and n. So if in this model we would like to find out the heat capacity, Cv, just like to differentiate this energy with respect to temperature. Now the ground state energy is temperature independent, so it is immaterial, it doesn't show up in the heat capacity, and then you're left with h bar omega and the derivative of this. So the derivative of this will be h bar omega over kBt minus 1 whole square h bar omega kBt, and then the derivative of this, which is h bar omega kb. There's a minus sign here, 1 over t square minus sign. So this minus sign goes away. So this turns out to be our heat capacity. I would like to plot this now. So if I were to define, h bar omega kb over kb, you can define this as another parameter. That parameter has dimensions of temperature, as is obvious. Let's call this parameter theta e for Einstein. So if we observe here, there is an h bar omega squared and kb t squared. So this term really is kb theta e over t whole square e theta e over capital T e theta e over t minus 1 whole square. So this is the heat capacity of a solid as a function of temperature. Now if you were to plot this with respect to T, given other constants, everything else is a constant for a particular medium. First of all, let's see what this curve looks like at high temperatures. At high temperatures, this term, when T is much larger than theta e, this term goes becomes very small. T is large, this exponent is small, so I can represent this exponent, this entire exponent by theta e over t, and I can represent this by 1 plus theta e over t. So all in all, so if for simplicity I just want to write theta e over t is x, so CV is kb x square. The denominator I just put 1 plus x, and I just keep it at the first order 1 plus x, so 1 plus x, so this becomes x squared. Okay, so this is 1 plus x minus 1, which is x squared. This is 1. This is already x squared over here. So in the high temperature limit, this term simply becomes kb. So the heat capacity is kb for a single oscillator. If I have n modes, I multiply this with n kb, and if I have 3 dimensions, I multiply this with 3. Okay, so the number of modes is n, the number of dimensions is 3, and this heat capacity turns out to be 3n kb. So all solids, independent of what the internal composition looks like, according to the Einstein model, all of them will have the same heat capacity at large temperatures. That is, at temperatures T which are much larger than theta E. This is called the Dulong-Petit law. It's an empirical observation. And if I were to plot the heat capacity in the Einsteinian model, CV, which is of course a function of temperature with T, I also need to look at the low temperature version of CV. So at low temperatures, you really need to find the limit of what happens to CV when T goes to 0. So if you use the L'Hopital's rule to solve this, this will turn out to be 0. So this curve for CV really looks like this. At large temperatures, it kind of asymptotes to 3n kb. Okay, and this n is the number of atoms inside the system. Okay, and it's right now we're assuming a monoatomic solid like copper, lead, iron, these metals, and all of these points, all of these CV variation will be described by that formula over here. By the way, this n, if I divide by the number of moles inside the system, by the amount of moles, so this n becomes Na. So this number of atoms per unit mole is 3Na, the Avogadro number. And Na into Kb is the molar gas constant, 3R. So this asymptotic line is really equal to 3R for monoatomic metals and solids. And it's quite remarkable that there's a single parameter. So this curve is defined by a single parameter, which is theta E. So if I vary theta E for a different solid, this curve might change. For different theta E's, it can have different forms, but it always asymptotes to 3n kb. So this is how the heat capacity varies. But this is a very poor model. Many solids do not follow this because we have used this density of states, which is very artificial. That there's only one frequency that exists for the phonons inside the system. So this has to improve. So far so good for this Einsteinian model. So there are two things that I really find interesting in this description. The first thing is that even though we have a solid and we're looking at oscillations of atoms inside the solid, we have this molar gas constant which is describing the high temperature behavior. So this represents that we are dealing these phonons as a gas of particles. The second is that the single parameter theta e, which is describing this behavior completely. Now, in order to move away from this naive assumption that we just have one frequency for the harmonic oscillator inside this vibrational model, we'll have to introduce another concept. And that is the concept of the density of states, which has to be looked at in a bit more detail. So let's move on to the density of states.